Eugene, I must say you just put on the best show. I mean, in terms of weather and campus, and I've heard fantastic things about you already. So that also means that please, ask questions in the middle. So and I'll paste the material I have on slides accordingly. The slides will be easily available, and I'll make them accessible in whatever you want to do with them. So, so some first remarks. That's not working because I have to turn it on. So the first thing I wanted to say is that there's some select references that I'll make available, and additional ones if you want to read them. I want to point out already something that might be different from what you've seen in the previous lectures. So if you look at the references there, some of them are very old, and they're from different fields. So two of them actually from accounting, and one of them is from ICFP, might be recognizable, and a couple other ones are from obscure, might to you at least, hopefully, conferences and journals. That's the ones where I'm on. So I hope you'll think of this as a way of pulling you into something or getting you interested in something that, from a programming language perspective, that is not exclusively rendered and presented to you from a programming language perspective, okay? So the second thing I have to say is that I know this is main theme is probabilistic programming, and I've looked through all my material, and okay, it's not in there. So, okay, so please don't wait for that part, okay? Now, the overview today, we'll just have a very informal introduction. You can already get a hint of that one because the slides are in PowerPoint, okay? So the next slides will be in LaTeX. They're going to be algebraic foundations for resource management. That's going to be tomorrow. And then we'll actually look at the composition of that and literally put those together into contracts, compositional contracts, and their management, their execution, their control, their monitoring. And the fourth part is that's Thursday afternoon. It's going to be late. It's going to be, I think it's going to be 2 o'clock. So it's going to be a little bit open. So I'll give you a little bit of work that we're doing right now on contract analysis and some other open issues, like the one I discovered on the plane over here, that what is the relation between, the linear resources we'll talk about in linear logic. So maybe I'll give an exercise to you because there might be one that's interesting to pursue. And other topics that maybe you, want to raise questions about. Okay, so who am I? So as I said, it's the first time I'm here, but actually it turns out almost all my students, PhD students, have been here. So Miguel, hi. So I'm really happy to be here. So my background is a little bit mixed. So I'm mostly working and have been working on various parts of originally foundational and then more and more applied aspects of programming language technology, ranging from basic algorithms to, high performance streaming algorithms and implementation, but also applications of that. And I think that's the great stuff we got into, to be honest, in the late 90s when we recognized that there's a lot to be done in informing systems and systems development in the real world, bringing in, you might say, some of the results, some of the insights, some of the knowledge from the 90s and zeros into, and now the 10s, into soft development. So background, as you can see on the right-hand side, we're also doing high-performance functional programming. So if you're interested in that, look up the Futhard page. It's related to some of what we're doing here because I'm not going to talk about it. It's how to value and risk compute various aspects of contracts. That's the combining theme of those two things. Okay, so all right, this is usually a first slide. It's not mine. It's actually Windsurf. Now, who here has heard of Windsurf before? Okay, this is a computer science bunch, I can see that. So Windsurf is, of course, co-designer, chief designer, you could say, of IP and TCP, the internet protocols that we use on a daily basis. And he used to be at the University of Purdue, so one would ask, why? That's interesting because he basically argues here is that we don't need it. Okay, but maybe I'm recorded here. So, but maybe it's actually a part of the story here is that blockchain is proposed and comes from a certain tradition originally, which is the cypherpunk movement, that is very anathema to many applications we have in the real world. So Minton is now, it's very important to know for this slide, he's now at Google. Okay, so if you look at it from a Google perspective, this is actually more the slide I think would be interesting to show in this setting. Because it's a little bit more refined. It's still the same. If you can see, if you graph the rotation, you will see there's a minor in there that corresponds. It's the upper link that corresponds to, onto the right, that corresponds to the one before. It's like, do you need to decentralize? Well, you know, I mean, if you have a trusted, good party, like, you know, a cloud provider with a very powerful stack of software, you know, and who has very elaborate systems to offer you, then, you know, it's a centralized, it's a privileged party that you entrust with, you know, running your systems, storing your data, observing your metadata, various kinds of things, okay? And, you know, if you have that situation, it's not a problem, it's not the problem itself that you formulate, oh, I need to have insurance management and blah, blah, blah. But it's a question of like, is this a requirement that we need to have a decentralized solution? I'll talk a little bit more about decentralization since it's the critical question here in a second. Let's assume we're not going, no, centralization is not important, and then if it's not important, you're lucky because you can go to the right, okay? It's very mature technology and systems and lots of programmers and, you know, engineers available over there. So the next question is like, oh no, now we've ended up in a situation where we have maybe a whole population or just a network, a business network of equals who don't trust each other enough to actually privilege one of them, right? Not even actually their own cloud provider to be the one who has more access to information and data than anybody else. So they want to be equals, okay? So, okay, so now they're going down there. So the second thing is, do we need tamper-proof logging? You know, what does that mean? Tamper-proof logging just means that storing data or storing updates to data, let's be a little bit, basically think of them as storing digital representations of events, okay? Now those events, you'd say, okay, they're stored someplace, okay? So maybe actually the system of equals here, they will store their own data and then pass them on to others when needed, right? And so we trust that they do that, okay? So if they do that, then we'll just say, well, it's not important that we actually tamper-proof it in the sense that it make it impossible to forge or even delete data after the fact, okay? So if that's not important, well, you'll go to the right, and you'll see familiar ways of just communicating. You have point-to-point messaging, and you're doing your REST-based programming as you nowadays do, or maybe you do various kinds of things where you basically query the state of a system. The system gives you some information. You say, oh, okay, that's the way it is. But imagine now you do want to have tamper-proof logging, for example, to make it incontrovertible what happened, to make sure that there's not just a belief in somebody actually giving you the right data, but there's basically a technical proof that they give you the right data after the fact, so they cannot change the data. So if that's the case, and there's a lot of situations where that is the case, what really happened in the past, let's look at this, well, look at these events here and look at the signatures on them, and these really happened because we have a trusted entry into a log of events. Then, you can't repudiate it. You can't basically say, it didn't really happen. So if you need that one, then we'll go down to the next one and say, okay, now we need a system, and very likely a system with hash pointers. They pop up all the time. Hash pointers are basically just data structures that you hash down into a short string, 256 bits, for example. And that one has a double property, namely can serve as a pointer. So you have a data structure that we can look it up. And if somebody returns a value to you and says, this is what it is, you can check whether they've actually given you the right data, right? So they're basically immutable pointers. And again, the platform guarantees they're immutable. So if you don't need to store resources in the system, you just have data. Think of data as information, and abstractly speaking here as information where nobody would be upset about duplicating it or maybe even losing it, okay? But this is losing part we said we don't want to do. Let's say about the duplication part. So if it's just data, so think of it, that's what people usually say when they say bits. It's just bits, okay? And if I send you a bunch of bits, and you know what's the final state of that? Anybody observing that one will see, oh, okay, I've sent you a bunch of bits, and they will usually assume that you received them. Well, you know, reliable message delivery is assumed. You've received them, and I still have them, right? So why wouldn't I still have them? So basically, I've duplicated, you know, those bits. I've duplicated information. So now you own it or you have it, and I have it. That's okay. Many situations where we have data, you know, an invoice, an instruction manual, book. Interesting. Already we get into this situation. The book contents you can certainly, you know, duplicate as much as you want, but maybe not the right to have it. Okay. So they're already be getting into a situation where maybe you want to prevent or manage actually the free copying of information. You don't look convinced.
It sounds a lot like DRM.
Okay. So, all right. Okay. Question. How about DRM? So think of me now talking as a tool maker. Okay. And I was praying and hoping and contributing to things being put to good use, but not really knowing whether they will be put to good use. Okay. So basically, all these techniques are actually, you know, in a general sense, dual purpose, okay? You can use them for a lot of different things. But you're absolutely right. DRM is relevant here because digital rights management will get us right into the yes corner of the left one here. Now, if you want to make sure, remember now where we are. You want to make sure we have a decentralized system. There's not a single organization or computational node that has better or worse access and control over the data than anybody else in the same network. So in that sense, truly peer-to-peer. Two, we want to have time-proof logging to be able to ensure there is a track record that cannot be forged. In particular, think about it in the sense that we have lots of parties involved who we now trust because they can't forge. Before we didn't really trust them. And the third one is now we want to store and transfer resources. Resources could be the most obvious resources, and by when I mean resources, think of them as like linear resources, okay? Things that should not be, in a trustworthy fashion, should not be duplicated, okay? Now, in the modern world nowadays, the most obvious thing we don't want to duplicate, and most difficult one, is actually yeah, who said it? Money, yes, it's money, okay? Money is, scary enough, is the most successful meme in the world. It doesn't really exist, but everybody believes in it. And the reason why everybody believes in it, because you can't afford not believing in it. So, as someone pointed out, it beats some other very successful memes, which I won't say on the camera here. So money is one of them. We want to make sure that it does have the property of whatever, how much you have once you transfer it, it is transferred. But then we have other things like a house ownership, for example, property that I own. You know, that's also digital rights management, you could say, in the sense that when I transfer my house, the property, the ownership over it, then it should be atomically the case that at any given point in time, one agent, we'll call them agents later on, will own it, but it should never be the case that two own it, okay? And actually we'll also make sure that it's not lost somewhere. Zero own it, okay? But it could also be ownership over certain, electronic book that you have, and it might actually be restricted, the transferring. So in principle it should be transferable, just like, in principle, the thing about money is that if I transfer money, you can transfer it on. I can't restrict that from you. But there could be restrictions for other things, like, I'll sell the house, but you're not allowed to sell to somebody else. That's kind of strange, right? And DRM was mentioned sometimes has the property that's not freely transferable, okay? And we'll actually worry about resources in the sense they are transferable resources, but freely transferable resources. Can be restricted, of course, okay. In the sense that if I give you a song to play, then you can play it, and if you want to give it to somebody else, you can't. You have to give it back to me, and I'll know who will own it then later on, okay. That would be one way of doing this one, and maybe not, I think as a computer scientist, maybe not the most elegant way of doing it, and there's other people who would say that that is also strange that, you know, why should a central party again know about who owns a particular piece of music? All right, so resources. So that's the story. Now my argument would be the following. Now think about this scenario, okay? Somebody says to you, got to build us a system. We need to have tamper-proof logging. It must be decentralized. And we need to have in that system stored things like money, access rights, digital representations of trucks driving around. I mean, digital representations of physical assets. And as I mentioned, of course, all kinds of money always pops up in economic transactions. Then I would argue, this is my argument here, is like, then that is basically the extensional characterization of a blockchain distributed ledger system. So there's a particular few of them out there in the world. They're kind of like in this design space. But I would argue that there's a huge design space out there that still can and should be explored. Okay, so what are the digital contracts pop up? Well, think about it this way. When it is about exchange of information, that's okay. We're usually interested in you give me this kind of piece of information or these data, I give you these data in turn. But where it really becomes important to ordinary people is when the thing we're exchanging, and exchanging really means two transfers at the basic level, right? I want to make sure that not only that you got my money and everybody's happy. Now wait a minute, what did I get in return for that, okay? Didn't I get anything in return for that? No, you just walk away, you're happy. Okay, that's maybe not the best kind of thing. So you want to have transactional properties in there too, which means that certain kinds of sets of events are good and some are bad, okay? So some of you would say, and you want to specify them. These are good sets, these are bad sets. And that's what we'll get to in the end. We'll call those contracts. And what makes them important, of course, they will involve transfer of resources, big amounts of money, big amounts of whatever, so you want to make sure that they have good properties. So let's talk about a little bit about these. So again, just to, you know, it's a decentralized in the sense that it has temporary reporting, digital, and it provides consistent, non-repudiable information across all principles. So, you know, people who are involved in this one. But we should really think of people as abstract entities, not as the nodes, computational nodes. This is the principles really that are engaged here. And it should provide against forging and double spending to be a believable platform, a trusted platform for anybody doing this one. It's very important to say that because usually you have one-on-one or, you know, very few people interacting with each other. Let's exchange things. The important part is not the three of us who are in agreement on that we didn't forge money or kind of duplicate money. That's completely irrelevant. It's important that anybody over here is guaranteed that we cannot here sort of forge money and duplicate it. That's what gives it trust. It's the effect on the outside. Okay. Organizational, technical. So technical decentralization, you could say, is almost a corollary of the second one. Almost in the sense you can always virtualize things, right? But the second part really says organizational decentralization. No single or select group of organizations has more or less control or access over the data and the processes that change them over time, okay? So in practice, you will see an important difference in systems design also. Some of them are non-permissioned. Sometimes you will say that that's when people talk about blockchain, okay? By permission means that the nodes and the operators of the computational nodes in the peer-to-peer system are authenticated, okay? And by authenticated, I mean really in the real-world sense of I know where you live, okay? So, which also means I know how to come after you, okay? And it's the other permissioning is that in the same fashion, the principles are also known to exist and have a home, and other people know where to find them. So that's sometimes called double permissioned. And the non-permissioned ones are actually the original ones in the sense where it was intended to be as anonymous as possible. So both node operators should not have to disclose who they are in that sense, nor actually the people exchanging money in this case, or Bitcoin or whatever, on the network. All right. So the hard part here in this area is, of course, now I'm going to the Swiss governance policy. So it just means that now, let's imagine we found a way of building this system up, and it's decentralized, remember? That's very important. Who has control over changing the rules of the game here, right? That should be almost by fiat, should also be decentralized, but how to do that? Okay, that's a sore point in many systems, and well, sore because it's inherently hard, practically and also theoretically. Okay, so let's have a little intermezzo, and this intermezzo is important because all of the next presentation I'll give here will be about that, okay? So, but just to give you a little bit of background where it comes from, and this kind of modeling, you know, people have always tried to understand, let's think of this as business transactions. So we're interested in business transactions. And remember, it's a general context in the sense it's not just about making sure that I give you money, okay? And boo, wow, that's wonderful, it happened. It usually has to do with the fact that I give you money and you give me money back in the future, so that's loans and there's financial contracts involved. And that's a lot of focus nowadays on those because they're purely digital resources that can be managed like this. But most actually contracts or implicit or explicit contracts are actually commercial contracts, okay? So which means that if you go into a bakery and you hand over, I don't know, 25 cents, no, that's not the case anymore, whatever, $1 to get, I don't know, a bagel. Huh. So that's an implicit contract you've entered into, and it's an exchange of money for a physical good, okay? Or if you hire somebody to do some cleaning or to do some, I don't know, solving your homeworks. No, wait, let's not do that. So there again, tool making. So that's again a commercial contract. So let's look at this one here. So the extended RIA accounting model is basically called a resource accounting model because it's not just keeping track of money transfers. So if you look at most ledgers, which are super interesting. Anybody ever done that? It's better than Stephen King. Looking at books, double entry, bookkeeping. No, it's not better than King, but still. Anybody done that? Bookkeeping? Okay, yes, so I see. No, didn't compete with.
Yeah, it doesn't compete with much.
Doesn't compete with much. All right, so the key thing here is then please hang on here, right? So if you've seen this before. So this is resource accounting. So by resource accounting, I mean we're not just accounting the value of something, you know, what I bought it for, we're actually accounting for the thing itself, okay? All right, so your accounts will contain that I have $14 and 2 bicycles of this type in this account, okay? Not just 14 times the purchase price of the bicycle, okay? And that's the basic RIA accounting model. So it has resources, I mentioned those. It has economic resources, they're called, just abbreviated to resources. Economic agents, that's the reason agent comes in. It's sometimes confusing. Think of it as a principal if you're from another domain, or an actor, somebody who facilitates something, you know. So it could be a person, a company, an institution, but it could also be an autonomous device if you think about it, you know, because an autonomous device is also somebody or something that facilitates something. In fact, you know, who knows whether it's a person or not who generated a certain event. It's an agent. A contract, which is not part of the original, not as elaborate as here, of the original model, so it has REA only, is a specification of obligations, permissions, and prohibitions. And we'll get back to that, of course, but they have to do with events. So events are economic events. Economic events, and the categories addressed originally in McCarthy's work is transfers and productions or transformations. So we'll focus on the transfer part in the rest, actually, but there is actually a way of thinking of these as a kind of statements. Think about it, many of the kinds of event statements you might want to have to describe what's going on in your business. I think this is, the reaccounting model is very, very nice because it basically just says, you just write down what happened, okay? I, bought a bicycle. By bought, I mean, I got delivered a bicycle from blah. And then I transferred money to blah. And he might make a reference to the first one saying, I did this in consideration of the delivery of the bicycle, okay? And you just write that down. So that's the reaccounting model basically. It's not double entry, it's just saying, write down what happened, okay? And the statements are transfers and transformations. There's internal. Transformation just means a production, sometimes called produces, okay? So the key thing about those things are, remember now, is that A transfers R to B. Think about it this way, if somebody writes this down and somebody, maybe that person validates it, it says, oh, it really happened. Then there is implicitly in that two things, namely A. In order for A to transfer R to B, A must have owned R. So somebody must have checked this prerequisite. B, after the event, the state is that definitely we can conclude immediately after this event that B owns R, right? And A does not own that R anymore, okay? So that's, but just, I haven't said anything about A, B, and R, just R is a resource, okay? And resource in the sense being linear. Now, A transfers R to R prime has the same reading. It just means that A is now using a resource, and resources can be compounded. In the sense, as I mentioned before, it could not just be $14, it could be $14 and 2 bicycle chains and another piece. That's a resource now. And then we could transform that by hiring somebody to put the pieces together into a bicycle, okay? Now what we can conclude in this one, the bicycle is a resource type, you could say. One bicycle of that kind is the R prime. And we know now that A, for this to succeed, it must have been the case that A owned R prime beforehand, right? Otherwise this couldn't be happening. And B, after it happened, well, A does not own R prime anymore, and A owns B. So this is basically, the two of them together are actually specializations of a general update of ownership. But that's the original ones from McCarthy. Now we've had these kinds of events, okay? Now we're interested in sets of events of these, okay? So without loss of generality, that's actually not quite true. I'll take it back. So we'll think of them as, later on, as sequences of events, okay? But for now, it just says a complex event is basically put together from these atomic events. And a certain set of those is a complex event. And now what is a contract? A contract basically specifies in some fashion, it specifies a number of sets of events that are good. So think of them as called happy paths. Now what's a happy path? A happy path is just all the sets that are good. So for example, if you have an exchange contract, bicycle for money, then a happy path could be first the bicycle delivered and then the right money paid. Another happy path could be first the money paid and then the bicycle delivered. So if I'm insisting on an order, those are all the happy paths. A sort of like, let me call it a sort of like, okay path is maybe some things happened, but the net effect of what happened is nothing. Okay, so we entered into a contract, and from the beginning, and then once we concluded, in the end, we can ascertain, I still have my money, you still have your bicycle. So nothing happened. Okay, think of it as like, that's when the contract didn't really succeed. I mean, we didn't execute it. Okay, or we observably didn't execute it. Okay. And the last is unhappy paths. Those you want to avoid. And those are very common in the real life, still to this day. Namely, I deliver the bicycle to you, you walk away. Like, hey, nice bike. Or you give me the money first, I walk away. Good to have money, isn't it? Those are two unhappy paths. Now remember, we said we'll leave out the empty one for now. So the happy paths are, a contract specifies the happy paths we agree to. Right? I don't know how much the bicycle is worth to me or not, but by signing it, we're saying those are the happy paths. And any other path, any other subset is not happy, okay? All right, that's basically it. So we're done. I saved myself 3.5 lectures, so that's great. Tamper-proof recording of events. I just mentioned this one. We won't get back much later on, but I think this is an exciting area for all kinds of people, whether you're interested in mechanism design or type systems or in linear arithmetic or actually in building IoT systems, because the events that I mentioned before are not purely digital events. Okay, they are physical events. So the key part about is now if we have a system that has these invariants that I mentioned, like you can't duplicate, that's a necessary but by far sufficient part from not cheating or doing something wrong. It just means that money is not duplicable, and trucks cannot be moved into two different locations, but they can be moved into one location, but in reality they're in a different location. Okay. So I can have a story at the digital level. This is the state of the world, but the real world is actually in a different state. So the key thing here is then for the events we require basically the following argument, is that the atomic events express something about the real world, okay? And so we need somebody who takes stipulate here that we have somebody who takes responsibility for filing that event. And it's non-repudiable, so you can't walk away from that later on. You can say, it wasn't an error, but you can't say it never happened. I never filed that, okay? That's the signature. And then the supporting evidence. It could be anything, really. But think about it this way. It's like, you're doing forensics later on. Somebody says, I say this happened, and what evidence do you have for that? It depends on the event you have, okay? The event could be a purchase event, in which case it could be, or cash receipt, I've given you cash. It could be a third-party validation, here's the bank receipt that says you transferred by bank transfer. Or actually, the parcel was delivered. The bicycle was delivered. Here's from UPS a receipt, okay? Something that says I'm giving evidence in support of my claim. So every one of those events is really just a claim that it happened, okay? And for the complex events, it's we're going to a completely different world. We'll say wait a minute. Let's just assume all those claims are true. Just classical logical reasoning. We never know, if you think about it. Logic's all about assuming things and then concluding something. You never know whether it's true or not, okay? Unless you're really in the field of tautologies. So you say, then we'll say, assume all those claims are true. Then all these events have happened, and they satisfy this contract that we've specified mathematically, because it's a happy path. And notice also, it also means that, if we then at the end, somebody ascertains that as a conclusion, it should be the case something has been delivered, but it's not in my garage, we can employ logic again and say, wait a minute, that means one of the assumptions, at least one of them, must be false. So we can go through the evidence and see which one, maybe multiple ones, did not hold. Okay, so I won't spend much time on the evidence part here. This is PL. We don't want to do with hardware. So, but this is just then the picture we get for blockchains as digital twins. So basically, they're like a movie of the world. Okay, so it cannot be changed later on. So you have the history of the blockchain is just a sequence of events, and something happens in the real world, and you just say, okay, I'll register that thing, and I supply a picture, some kind of evidence. And in this fashion, the blockchain down there makes sure that this is actually the registered events. Later on, people cannot sort of go back and redo the movie. And the key thing about the contracts is now, and at this point I want to mention this one, if this event happens as part of the execution of a contract, so if we're trying to find a happy path, remember there's something still to be done. It's like a movie script then, right? Okay, so this is the movie we've shot. This is where we're actually shooting right now. But we have a contract. A contract is like a manuscript. So we don't just like, oh, anything can happen. No, not really. The manuscript says that either actually we're going to replace the car, or we have to repair it, okay? So, okay, so that seems like that's the continuation of the movie. So at this point, actually, if somebody asks you, what's going to happen now? You have an explicit contract, you have a presentation, a specification of a contract. What's going to happen now in the future? In the future, not what happened in the past. You can say, let me look at about all the things that happened in the past that these people were involved in and so on. And I don't know, I have about a billion records of these, and I have a model. I can maybe infer, like 1,000 or 10,000 parameters. I can guess myself to a couple of things using just standard machine learning nowadays, okay? But you would say, that's a tough job. Why not take actually the contract into account? Because if you know the contract, you know not all kinds of things can happen, because a specific contract here, specific continuations are possible in the future, and then you can still employ machine learning to say, like, most people chose the first choice, but you have a much smaller kind of space of possibilities in the future. That's all future work. So, digital resource management. Now I'll keep on going until a couple more minutes. So systems keep track of ownership of location resources, and what that means is that, as I said before, now what I'd like to offer to you is like a way of splitting this kind of digital resource management up into two parts. Okay, the first one is resource preservation, and the second one is credit limit enforcement. Sounds artificial, but it's actually, I think, a very useful distinction. So, resource preservation means that imagine now you have a world of ownership. Somebody is managing resource ownership, okay? Now that somebody could be physics, law, and whatever. So if you think about cash is being managed by physics, legislation, and various kinds of things. It's not like a single agent, because cache, locations where cache is there, I don't know, not known to anybody really. But there is this kind of belief we have that if I hand you cash, then, the sum total of cash has not been changed. So the key invariant here is that I might be doing right or wrong things, but if there's a transfer of money, of a transfer of a resource, the sum of resources that are in the system, owned by anybody, is invariant. It's the same. Okay? So if A transfers 50 ether to B, then the sum of ethers in the system is still the same. Okay? And of course, if it succeeds, it's one of two ways. It's atomically the case that you get minus 50 down on one account and plus 50 in the other. Or if it doesn't succeed, 0, 0, okay? Now, credit limit enforcement. Okay, so this is the thing, of course. If you think about it, if we allow negative balances now, so from here on, you got to think of it as saying, balances, we're not in the domain of natural numbers. We're not in the domain where we have to struggle with monas and all kinds of things. We're in this domain of groups, modules, vector spaces, okay? There is always additive inverses, okay? So for now, think of it as like the integral numbers or real numbers, okay? They occur, so in other words, you can own something, you can own minus 20 or something, okay? So credit limit enforcement means like a transfer is only valid. So that's always possible in resource preservation. All transfers are possible and they preserve the balance, okay? Some of those then will not be accepted because they violate maybe a credit limit that has been imposed on individual agents, okay? So, transfers are and affected then if the credit limits of each agent are respected. So, for example, if A owns 60 ETH and has a credit limit of 0, then it's valid, okay? So we just, remember we're transferring 50 away from A. So yeah, that's because, I have 60 in my account. So, afterwards I have 10. Now A has 30 and has a credit limit of 0, not valid. Okay, so the whole transfer is not valid. By the way, I mentioned there's, of course, possibility of doing partial transfers here. Curiously, in the real world, they're not done. I have no idea why, but for some reason they're not done. They would make a lot of sense. But and the other one is like you have the 30 ether, but you have a credit limit of 20. In that case, which means that your account balance can go to minus 20, but not lower, the 50 transfer is valid, okay? And after that, you own minus 20, and the other counterparty still, well, has 50 more. So, no double spend guarantee, that, who's heard of the no double spend guarantee? Okay, so that's the number of people awake. Let me just count. All right, okay. Okay, I'll speed up. So that means that a UTXO is sometimes an unspent transaction output, but you can think of it as like as an account that has a balance, and you cannot just pull out money one at a time, but you're forced to spend the whole thing. But the funny thing is, you can always open a new account. So if you want to keep some of the money in your account, you just transfer the amount you want to transfer to somebody else, and the rest you transfer to a newly opened account. That's a UTXO. Pardon?
What does UTXO stand for?
Oh, it stands for unspent transaction output. Thank you for the question, because it's one of those terminological things that came from this subdomain of Bitcoin, actually. So the full reserve monetary system actually can then be explained as there being no money at all. The balance is always zero, nothing. In fact, that's the great thing about fiat money. Fiat means like invented money, the money we have nowadays in almost all places. The money is not backed by gold or anything. It's invented on the spot. And the thing that does it, for example, if you have a central bank, it says there's no money in the world, but I have no credit limit, okay? So I can just transfer money to you. Now you have money all of a sudden. I'm in the minus, and I can transfer more money to other people, okay? And I can go deeply in the minus. And if I'm the only one who's allowed to have a negative balance, the central bank, that's called full reserve banking. How many countries do you believe use full reserve banking, which means that everybody, yeah. All of them? Okay, I would say presently none. So Iceland has been debating it. It's been discussed in Holland right now as we speak in Parliament. It's been discussed in various places. Holland, I said the Netherlands. And so the fractional reserve system is actually what we're using nowadays, which means that there's a designated set of agents, all of them called banks, including the central bank. But all of them are banks in the sense that they're licensed to have negative balances, okay? So they're the ones who are allowed to print money, okay? So not only the central bank, but also all ordinary banks, they can just print money. Okay, so and of course you can also say that if I get transferred a car from somebody and it's the producer of those cars, you would not be worried about, do you even own a car? And validate it, you'd say like, I'll just assume you can produce one if needed. Okay, so commutativity theorem, it says if every agent has an infinite credit limit, then all resource transfers are valid and can be executed in arbitrary order. You've seen that already actually, because there's no validation necessary, okay? And the key thing is also, maybe I should mention, if you have a number of transfers going back and forth, they fully commute. You can do them in any order, okay? Any order whatsoever. There's no reason to order them to a single order, like, carefully, this order, executing them. I can do it any order. Maybe we have 16 nodes, and I get them in this order, you get them in the other order, doesn't matter. We're eventually consistent. After 16 transfers, we just count how many unique transfers we've seen, then we'll have the same account, even if we get to see them in a different order. Corollary is that we actually, consensus-wise, so if we have, the ones involved here have infinite credit limit, and we're maybe the two of us actually interacting, we don't need to tell anybody about our interactions. Whether or not we have a contract does not affect in any way anybody else and anybody else's ability to enter into a contract. Because we have infinite, so if you promise or if I promise something to you, after giving away most of my money to somebody else, it doesn't matter. Infinite credit limit, my transfer to you is always valid, okay? So of course, so the commutative part, it's a if and only if. So if one of us has, or maybe both of us have credit limit involved, we have to leak information about our interactions. It's not possible that no information is leaked to anybody else, because the argument is simple. If I pay you, and you say, oh, that's good, thank you very much, but you don't know whether I've paid you after giving all my money to you in a secret transaction or not. So if it's not observed, nothing is observable about our transaction here, you wouldn't know whether I've breached my credit limit or not. So something has to be leaked. And total event ordering. Let's take a break because it's really a long session. Okay. For the rest, there's not too much. So total event ordering is very often used actually to establish credit limit enforcement, really, okay? So what does that mean? In distributed consensus, you have a network of nodes, and the nodes receive information, in this case events, and their job now is, let's declare that to be, that's total event order, is collectively they have to agree on a single sequence of events, okay? So they're coming in, but any single node has to have the same view of the set of all events that have come in. So the same sequence of events. So that's a very hard problem. So the key thing is that that is sufficient for resource transfer validation. So first all the nodes actually agree on a single sequence of events. Now we have a sequence of events. You can just take one event at a time and see, okay, somebody wants to transfer money. Well, at every given point in time, I have the account balances for everybody. I have their credit limits. I'll just check it. Is it satisfied or not? If not, it's not valid, doesn't get executed. Next one, okay? And all nodes do the same thing because they've agreed on the same sequence of events. But it's not necessary for resource transfer validation. So that's being recognized more and more, is that actually, I would put it the other way around. So this is actually how you just like first solve total event order problem, and you could say that's the hardest problem involved here. Once you've solved that one, let's say freshly, you've spent 99% of all resources on that. The rest is trivial, but maybe you don't have to solve this problem, okay? And let's observe, actually, total event ordering is not necessary from a resource transfer validation. We've already seen without credit limits, no event order has to be. Any kind of execution order is okay. And in other ones, you can exploit certain properties that mean they have still commutativity of events. So if you transfer A, B, R, and C, D, Q, well, you know, if they're all different agents, you know, the order doesn't matter. So you can do all kinds of optimizations here in the sense that you have all the transfers involving A's and B's and executed differently from those from C and D, because then any merge of those two will be giving the same result. Okay, so in other words, you don't have to have a total order at all. At most, partial order. So I want to point that out because that means that already, if it's only about keeping track of the resources, maybe it's not necessary. Maybe it's possible to have a much more scalable resource management regime in a decentralized setting. All right, business architecture with intermediaries. So actually, this is actually motivating now how we deal in the real world, you could say. So you have a company, you have contracts, and there's some third parties involved in the contracts that help us execute the contracts correctly. They arbitrate, they help us various things. There could be multiple third parties, like the delivery company we saw before. But think of them as like, you know, a single third party that helps us. There's also resource managers involved there, namely the ones that keep track of ownership of resources and validate a transfer before we actually believe it happened, okay? So, you know, here it's like, you know, the banking system. Here it's like one of the land registries that has existed 500 years. And And here's my, a car ownership registry. So we have trusted third parties involved. Now, the blockchain architecture basically tries to mirror that a little bit, okay? But there's a couple of differences. The classical blockchain, there's Ethereum style, I would call that one, looks like this. You have, well, resource manager, and it's a single black bar here. It's a single resource manager. And you have a single blue contract, smart contract here. Blue means public, everybody can see it. Not just the two parties involved, okay? And here you have another one, smart. But also notice that there's the red box was missing. So it turns out the smart contract is a third party, and it executes certain steps. It must make certain steps, but there's no explicit rule book anymore. Okay, it's just code. Well, if you think about it nowadays, it's code. And this is actually what you think of it. So what does a smart contract nowadays look like? It's basically a program. Okay. So it doesn't have to be like that, and I'll hope to convince you of that. But it right now is a distributed append-only transaction, so it's a total order event log that's maintained, and then smart contract, the code it's like a class in a Java-like language. Once instantiated, you get an object. Well, that's a running smart contract. And the object messages are just like ordinary messages in object-oriented languages, with one difference. Now, namely, they include linear resource transfers. You can send something, and the something you can send is a single currency item. So in this case, Ether, when it comes to Ethereum. So smart contracts are Turing complete, usually written in a language that is expressive and familiar. So wonderful. Also, public blockchain systems very easy to get access to, so it's very easy to program something up and get it running. But they're sort of, I would call that very undecidable, okay? By that I mean not just undecidable in the ordinary sense, but if anybody's worked in static analysis or even anything else, very, very hard, or cumbersome, or both, to get safety information about. So in particular, and here's the thing, this is wonderful for programming language people involved in static type systems, in safety analysis, in static analysis. Smart contracts are wonderful for us because they don't just move bits, they move money. All right? That's the great thing, is like they move money and you can't take it back. It's like somebody once said, it's like, writing some of these languages is like writing JavaScript, but with JavaScript having direct access to your bank account. So it's still just JavaScript, right? Yeah. But now people are more interested, of course, in what about the safety and quantitative and qualitative safety arguments. We'll come back to that. So of course the other part is, of course, then clever people who know how to find bugs are also the ones that can write programs where the bugs are in there but cannot be found. Okay, so okay. There's a lot of vulnerabilities in Ethereum. So who's heard of Ethereum before? More people awake. Thank you. So we have transaction order dependence. So messages may have different effect depending on their order of arrival. So if you have that's a common, that happens in contracts all the time when you write them. So as the contract writer, you have to be careful. That shouldn't be the case, because once it's the case, you have actually front running made available. So in other words, somebody observed there's a message coming in, and you can't stop it anymore. It will get processed. You might as well just intercept, put in your own message in between to update, the object, so maybe you get the prize instead of the one who's about to claim it. Timestamp dependence. So smart contracts have different executions depending on the timestamp on a transaction block. Well, who sets the time? Again, there is no global time, so somebody sets the time. Okay, so a miner might set the time, saying, it's very convenient for me to put this to be now to be Tuesday at 9 p.m., not 9:12, because then I can still sneak in another event. Exception handling, gas management, they're very fragile. There is a number of subtleties with dynamic method forwarding that have led to exploits. And instead of saying this many screens went blank, nowadays you always hear it's like $150 million lost or whatever. So as you can see, it's not the number of bits that went that have the wrong shade, but it's the number of money that doesn't arrive in the right places. Reentrancy vulnerability, I will skip that a little bit. Who's heard about one? That's also old, so yeah, that's a classic. We can talk about this next time if you want to. But so the thing I wanted to lead up to is actually another architecture. Namely, it says that, look, the red part means that these are a priori, private to the two parties involved. So, you can't have a secret contract. I have a contract with you, but I'm not going to tell you which one. So it's shared in that sense, but I don't need to share it with anybody else from the outset. And then there's a contract manager then, which you can think of as a generic smart contract, a program that executes and monitors the correct execution of a contract. But to make it actually more realistic, this is actually the one that you end up with, and you have to end up with. Because, the resource managers mean they're very nice to have, but you cannot expect to have a single resource manager, a single decentralized or a centralized system that manages all the resources in the world, okay? So all the houses, all the music, titles, all the money, fiat and ether and Bitcoin. So clearly, actually, we'll have a situation where we have some resources managed actually, maybe in a blockchain system. It's very nice. It's decentralized. It doesn't have a privileged party. And some of them actually we do want to have or still have privileged parties, like the banking system or a public system that manages, and we believe in it. I'm in the US here, so yeah, many of us in Europe, we believe in actually government stuff. So we have systems. But as I said again, if you don't believe in it, well, maybe you would be more interested in a decentralized system. So this is more a contextual requirement. So, but the key thing is that they have the same functionality. Namely, they validate transfers and effect them. Okay. So what are the consequences? Let's look at this. Okay, so this was the picture, and I was trying to motivate it before by saying that this is not accidental. Okay. Here you have a contract manager. Think of it as a person or a program now. Okay, it's somebody who does something. That one's generic here in the sense that the first thing you do is company A and company B entering into a contract, multi-party contract. I mean, this is a simple picture. It could also be 100 principals or people or whatever, okay? They first enter it. The first thing they do is they hand off the contract to the contract manager. The contract manager is generic in the sense that it says, I don't know which contracts to manage for you. You better hand it to me first. But once you've handed it to me, I'll make sure you abide by it, okay? And I can give you a couple of variations on that. We'll get to this one 2 days from now. Namely, I can also offer escrow management, for example, if you want to have it. But my buddy over here doesn't do escrow management, also manages the same kind of contracts, and just monitors them. And the buddy over here does actually mark-to-market collateralization of the same contract. So you decide which contract you want to enter into, and separately, and it might change actually, change which contract manager. We all do basically the same thing, and the basically same thing means make sure the happy paths get correctly achieved. But we might actually do a couple of different things depending on your needs, okay? That's the key thing is we have a separation of the contract per se from the contract manager. Now, if you thought about the picture before, you would very often write the contract manager. This is code, right? And then think of it as an interpreter. It interprets the contract. And then you say, we might as well specialize it. Who's heard of specialization, partial evaluation? Okay. So basically, it's a way of saying, let's compile it into the language. And then you get something that has only a single box. And you conceptually can think of that one. That's the handwritten part of somebody who has written an Ethereum contract, okay? We try to, but conceptually we keep it separate because then we can also analyze these and these separately from each other. Okay, and of course we need different, of course I'm saying, I claim that we need different resource managers where the contract managers then are actually the transactional glue that makes sure that, you can pay in a banking system for a house you get transferred. in such a way that you get the house if and only if you get, you pay the money. All right, so we have a separation of contract lifecycle management from contracts. So the contract lifecycle management basically means that, okay, you've entered into a contract. It could be a 40-year contract like a pension plan. All right, so I'm just making sure that I know at every given point in time what the state of that contract is. It changes, as you've made a premium payment or not. Of course, it changes, it has state. Then the contract lifecycle managers, they can be generic, which means like, they can manage any contract. In particular, the same kind of contract manager can be written in many different programming languages and to be running on or with different resource managers. So, for example, write it in Kotlin or in Go or in Java and Haskell, all of them, they might all actually then manage the same contract. And the separation of resource management from contract management gives us two increasability. And this is open. I mean, we're trying to work on this one. Gives us, a handle on drastically improving, at least for permission systems, scalability that's been so bad until, okay. Namely, the first one is event log per contract. So notice that we only need to make sure that as a contract manager keeps track of what happened on any given individual contract. So if you have 100 million contracts running at the same time, or 10 million, they just managed completely independently of each other. Almost, okay? As I said, the credit limit enforcement, right? So, but in principle, you can think of it as like, there's just 100 million threads, or 10 million threads, and each one of them is managing their own contract. Or maybe there's 1,000 threads, and each of them managing, 10,000, contracts then. We can scale it out like this. The other scale out is that if you look at the resource parts, I already mentioned, the resource parts only have to do with transfer of information. Transfer of resources. And transfer of resources has lots of commutativity properties. We can also use that one to basically partition, these out in various fashions. And I'll give tomorrow an example of how to think of this one, mathematically. And then you can see actually how you would maybe do some partitioning of the resource management such that you get good scalability instead of having a single system where everybody has to send their resource transfers to. And so, simple privacy in the sense that, if you communicate messages to each other, you just don't need to show them to anybody else, okay? You still need to encrypt them, of course, once they leave the system and so on, but it's not like necessary from the beginning. And as I said, we'll get the mathematical semantics of contracts, which is a domain-specific language, much smaller than a full-featured Turing-complete language. So we have observations that I'll not bother you with. So the observations and open problems, I would say, is the ones that I mentioned here. Is that there's still an enormous amount of space possible in improving scalability and starting out with a private by design architecture as opposed to public by design. I'm out of time, but we have a platform going on at Deco where we're exploring these ideas to have maximum sharding and having this implemented for contract specification language that we have developed for a while now. Since I'm out of time, skip this one. And just say that tomorrow we'll look at resource transfers a little bit more formally, actually quite a bit more formally, okay? So thanks for your patience with a rather informal overall introduction to the scope of blockchain and distributed ledger systems. Thanks.